Hello, and welcome to this on-demand session for Build 2020. My name is Sean McKenna, and I'm the lead PM for the Azure Kubernetes service. In this session, we're going to talk about some Kubernetes best practices, and specifically what we're doing to make those best practices more discoverable and actionable within Azure and AKS. I'm going to walk through three areas where we're exposing best practices. First, we'll talk about how you can use the recommendations in Azure Advisor to improve your overall cluster hygiene. Next, we'll look at Azure Security Center and how you can use both the security posture recommendations and the threat detection alerts to harden your Kubernetes environment. And finally, we'll look at how you can apply some best practices in terms of how you troubleshoot what you may be seeing with AKS diagnostics. Now, in this session, we'll only be able to touch on a handful of best practices recommendations, so I'd encourage you to check out the full set of content we have available at the link I provided here. So first up is Azure Advisor. Azure Advisor provides a way to offer proactive recommendations for your environment based on our knowledge of Kubernetes on Azure best practices and the telemetry we have for your cluster. We currently offer 5 recommendations related to pod disruption budgets, expired service principals, and cluster certificates, unsupported Kubernetes versions, and missing OMS workspaces. We have a lot more planned, including some that directly address common issues with Kubernetes resource management. Now, the idea with these recommendations is to make you aware of things you should be considering in your environment and provide suggestions. However, how you consume and apply them will be a function of your specific situation. To illustrate that, let's look at a couple of specific examples. First, let's talk about pod disruption budgets. So, pod disruption budgets are a feature of Kubernetes that allow you to inform the Kubernetes scheduler about the availability characteristics of your application that it can take into consideration in the event of voluntary disruptions within the cluster. Now, what do we mean when we say voluntary disruptions? Well, these are events that might happen as a result either of a direct action by a cluster operator or at least by the natural operation of the cluster based on some configuration that the cluster operator has provided. So in a managed Kubernetes environment like AKS, the most common examples of voluntary disruptions would be Kubernetes upgrades, where the scheduler needs to move pods around as nodes are getting upgraded, or cluster scale down, where again, the scheduler needs to move pods between nodes as it's looking to pack the workloads of the cluster into a smaller set of nodes. And so what you can do with a pod disruption budget is tell the scheduler either what the minimum number of pods within a deployment is. So if you have a absolute minimum bar for the number of pods that you need to have, or conversely, the maximum number that you can have unavailable within that deployment or within the selection criteria for that budget. So some of the common use cases for this are limiting the reduction of the application capacity on a stateless application. So if you've got a web front end that could tolerate only, say, 20% of decline in capacity as part of the voluntary disruption, the activities in the cluster, then you might say that your max unavailable for that selection, for that budget is 20%. You can use it to block disruption to stateful applications of which there may be only one instance. So if you have some application that's not capable of being replicated, there can only be one instance of it running at a time, then obviously any movement of that pod is going to result in downtime. So you can use a pod disruption budget where you say max unavailable for this is 0. And that will actually block any movement of that pod between nodes, which effectively means that there at least needs to be some conversation between the cluster operator and the owner of that workload before that thing gets moved, because it is going to result in downtime. Then if you have a replicated stateful application, you can use this as a way to declare what the quorum requirements might be so that you ensure that even as pods are getting moved between different nodes, you're always maintaining that quorum and can continue to accept writes against that data store. So just a few of the common examples that you might use a pod disruption budget for. And this is the type of thing where this is a capability of Kubernetes. It's a critical thing that you describe to the scheduler, because it's going to be a constraint that you want to have honored in the ongoing operation of the cluster. But it's not necessarily something that you would come across as part of learning Kubernetes and starting to adopt it. And so this is the type of thing that we're trying to expose through tools like Azure Advisor, so that you become aware of it, you know that it's something that you should consider, and you can go dig into and think about how it applies to your specific workloads. Okay, so now that we understand what pod disruption budgets are and how they can be leveraged to improve application availability in the context of voluntary disruptions that might happen within the cluster, let's take a look at how they get surfaced in the experience and how we can actually apply them to a real cluster environment. So we surface advisor recommendations through a few different entry points. So obviously the Azure Advisor user experience provides advisor recommendations across all of your Azure resources, including AKS. If you want to see just the AKS recommendations, you can see that through the AKS blade here in the portal. So here under monitoring, I can click on advisor recommendations, and that will show me the ones that we've discovered for this particular cluster. So you can see a few here that are actually surfaced from Azure Security Center. We'll talk about those in a little bit. But then the third one is pod disruption budget. So if I click on that, you'll see that it gives me some recommended actions here. So I can click into this, and that'll send me off into the Azure documentation. It's going to show me, it's going to review again the information we've just discussed in terms of the scenarios where PDBs are useful, and then give me some samples here that I can leverage to apply them into my own cluster. So now let's take a look at how that knowledge of PDBs and that recommendation from Advisor can be applied in a real cluster. So I've got a cluster here with a deployment running that's got 3 pods. Those pods have been spread across 3 different nodes within the cluster. And at this point I have no PDBs applied. So there's been nothing to inform the scheduler that as I'm performing various operations in the cluster that it needs to be mindful of what my availability targets are for this particular application. So to illustrate the impact of that as I might be invoking various cluster operations, whether it's a Kubernetes upgrade or a scale down operation, we'll just go ahead and perform a drain on each of these nodes in turn. So we'll do kubectl drain one of those nodes, and I'm going to say ignore daemon sets. Daemon sets naturally are running 1 per node, and so they're sort of inherently they inherently object to a drain operation because they can't be moved elsewhere. And so we have to say that that we're okay with that. And so I'll say drain, and you'll see as I do that that there's going to be a blip in one of those pods as it gets rescheduled to a different node. So now I'm in a state where I've got two of those 3 pods running on node 1 and another one on node 2. And so now if I drain node 1, I'll see another blip as those 2 pods running on node 1 move to node 2. And now I've got all 3 of them running on node 2. And now, most interestingly, when I attempt to drain node 2, I'm actually going to move into a state where I've got no nodes available to run this deployment. And the scheduler is not actually going to stop me from doing that. It has no awareness of the availability guarantees that I'm trying to maintain for this application. And so it's going to assume that I know what I'm doing in draining that node and move those pods into a pending state, which basically means that they are awaiting a node to be available to be scheduled on. So as a result of doing this, I'm now in a fully down situation. There's no pods available to serve traffic for this application. They're all sitting here in a pending state. So this is the type of thing that a pod disruption budget can help protect against by virtue of signaling to the scheduler what the guarantees are that I want to maintain for that application. So to illustrate that, let's just do a uncordon one of those nodes. So we'll just bring back node 2. And as a result of doing that now, there is a node available for those containers to be scheduled on, or those pods to be scheduled on, and so you'll see they come back into a running state. Now, to illustrate the difference between not having that PDB and having it, we will go ahead and apply this pod disruption budget. You can see is fairly simple. Just got name, namespace. I'm going to say that I want to have at most one unavailable pod within this particular selection range, and by virtue of doing that, the scheduler is going to respect that availability request. So if I go ahead and apply that now, and now try to, again, drain that node 2, you'll see that it surfaces an error to me here, that it's not able to evict those additional pods because it wants to maintain the availability guarantee that I have signaled through the PDB. So you'll see it has evicted one pod, so one has moved to a pending state, but 2 are going to remain running because I had said that I wanted to have a maximum of one pod for that selection criteria unavailable at any given time. So this sort of illustrates the types of constraints that you can put on the scheduler to protect you against unintended availability loss as a result of some of those activities that you might be performing within the cluster. So the other advisor recommendation that I thought I'd drill in on is around unsupported Kubernetes versions. So I'm going to talk a little bit about the cadence of the Kubernetes project itself, how that's being reflected in AKS, how we consume new releases into the service, and why it's important for you to stay up to date. Then I'll talk a little bit about the upgrade process, as well as an alternative best practice that we've seen a lot of customers follow around using node pools for consuming new Kubernetes versions, and some of the work that we're doing and capabilities that you can take advantage of if you're looking to follow that best practice. So the Kubernetes project is fast moving. It is shipping new minor releases about every 3 months on a fairly consistent cadence. So the most recent release was 1.18 at the end of March. 1.19 is scheduled to be released at the end of June. So those are minor releases. Patch releases are then shipped as required for bug fixes and security patches. So this is 1.18.1.2 and so on. In the upstream project, only the latest release and the last 2 minor releases are supported. So at any given time, you've got roughly the last 9 months of releases being supported, up to the last 9 months of releases being supported. And what this means is that if you're running a version that is older than that, you may be running one that has critical security vulnerabilities, certainly potentially performance issues and other bugs. But security vulnerability is obviously the most important here. And what we've seen is with the growth of Kubernetes, it has become a greater target. There's been a notable increase in the number of CVEs that have been highlighted over the last year or so, and so it is that much more critical that you're staying up to speed with Kubernetes releases as they come out. So in AKS, we try to stay up to speed with the upstream project as much as possible. So we have mapped our support matrix to that upstream process. So we also support 3 minor releases at any given time. And the way this works in terms of the process is you'll see a new minor release or new minor version released upstream. Typically that'll be incorporated into AKS within a matter of weeks as a preview. And at that point we will announce the pending retirement of the oldest minor release after 30 days. You have 30 days notice if you're on that minor release to move forward before you fall out of support. After that 30-day period, we graduate the new minor release to a G8 state, and at that point drop the oldest one off the back. Now, it's important to point out that clusters that are running those older versions don't stop working. The applications that are still running within them remain available. However, you do have potential vulnerabilities that are running in there. You're not going to be able to consume new improvements that are shipped. And if you do create a support issue, that's something where customer support will typically ask you to upgrade to get onto a supported release, as there's obviously a lot of changes that go into these releases every 3 months. So how do I actually consume those upgrades? Well, as a managed service, AKS provides a first-class upgrade capability. So you have the ability to upgrade the cluster either as a whole, so both the control plane and all of the associated node pools, or you can do that individually. So you can invoke a control plane only upgrade and then work your way through the node pool, so you have full control over those versions, with the only caveat being that the control plane always needs to be at the greatest version within the cluster. So the node pools can be behind, but they cannot be ahead. Now, of course, it's the node pool upgrades that are the most interesting, and that's where we get into the value of something like a pod disruption budget. So the way that those work is we initially will add a new node into the cluster, into the node pool with the target version. So if you're moving from, say, 116 to 117, the new node will be based on 117. Then we will pick one of the older nodes and perform a cord and drain operation similar to the one that we just saw, where we'll try to drain all the existing workloads off of that node and move them elsewhere within the node pool until that node is completely empty, at which point it'll be removed, a new node will be added, and then that process continues until all of the nodes have been moved forward and replaced with ones that are running on the new version. Now, obviously, that fully automated upgrade process is very convenient, and for a lot of scenarios it works beautifully, but there are certain use cases where it has drawbacks. So first of all, for very large clusters, it can be slow. So as we're following a node by node upgrade process and requesting that each of those pods gracefully terminate, that is something that can take a certain amount of time, and then at the very least it is out of your control. So you don't have the ability to manage the creation of the new nodes or the ordering of draining of the old ones. And so if that's something where you want to have a little bit of more oversight as part of the upgrade process, the built-in upgrade experience doesn't allow you to do that. So what we've seen is a lot of customers end up following an alternative approach using node pools, where rather than running that node by node upgrade, they will actually create an entirely new node pool targeting the new Kubernetes version. So again, maybe a new node pool targeting version 1.17, and then they will drain the nodes themselves on the old node pool, which will force the rescheduling onto the new nodes, and then once all of that, all the old nodes have been drained, delete the node pool. So at a high level, it is effectively following the same process the built-in experience does, but you're able to create all of the new nodes as a single operation, and then control the ordering and the timing of draining of the old ones. So you could drain a handful of nodes, get the pods rescheduled onto the new nodes, make sure that everything's running correctly, and then continue with the process, as opposed to having completely outsourced that to the service. So with that in mind, we've been making a bunch of improvements to our node pool support. So the first one is we've introduced the notion of node pool types. So the background here is you have a set of system services that need to run on your node. So this is things like core DNS and its autoscaler, metric server, the tunnel, and others. And those are services that are critical to the health of your cluster. And so they need to be kept running. They need to have dedicated resources. And so it's typically a best practice to isolate those components into their own nodes, so that you can then run your applications completely separately from them. And so we've now elevated that idea into a first-class concept where you can signal that a particular node pool is a system node pool, and that's the default one that gets created with the cluster, and then subsequent node pools can be created as user node pools to run your application. So it creates a nice way of segmenting the different workloads that are running within the cluster. Within user node pools, you can use those to run either Linux or Windows pods. They can be made up of either spot instances or on demand. We'll talk about spot here in a second. And then critically, they can actually scale down to 0 nodes. So while for the cluster to remain available, those system services that I mentioned need to continue to run. Your application, if it doesn't have any work to do and can actually scale down to nothing, you can likewise scale the associated infrastructure down to 0. And so you can really manage that that set of resources associated with your user node pools. We've also added the notion of spot node pools, and so this is built on top of the Azure Spot capability that became generally available recently, and this is an evolution of the low priority capability that we had previously within VMSS. And so the idea here is to allow you to get unused Azure capacity at a pretty steep discount, so up to 80% in some cases, while being mindful of the fact that capacity is not guaranteed. So if it needs to be reclaimed for other customers who are willing to pay full price, then your nodes will get evicted. But for certain workloads, namely things that are maybe lower priority and certainly things that are very tolerant of interruption, so batch jobs, machine learning type workloads, this can be a very nice way to get significant discount on your compute costs while still running in an AKS environment. We recommend that you associate the cluster autoscaler with a spot node pool such that if a node does get evicted based on capacity constraints, that the Azure Fabric can attempt to redeploy it elsewhere within the environment, which will show up as just a new node within your node pool. And the autoscaler can manage that process for you. So just a couple caveats here. One is that spot node pools cannot be upgraded. So because of the way that we run that upgrade process and the need to provision new nodes, because we can't guarantee that those new nodes will be provisioned in a timely fashion, we won't allow you to start an upgrade process. So you should think of these spot node pools as being effectively tied to the version that they are created with, which then ties back into that best practice around performing upgrades via a new node pool creation. And then they cannot be used as system node pools. So obviously we want to have dedicated resources to run those system services, and so spot node pools should be really reserved for user applications. Okay, so that's Azure Advisor, which is really about giving you general cluster hygiene recommendations. Now let's drill in on a specific area of interest, which is security hardening within Security Center. So there's a specific offer within Security Center for AKS services, AKS clusters. If you've opted into that within your subscription, then every new cluster and the associated resources will automatically come under Security Center monitoring. And much like Security Center does for other resources in Azure, it's really going to provide two benefits for that AKS resource. The first is looking at the cluster configuration and determining if you are following security best practices and giving you recommendations for ways to improve your security posture for that cluster. And then it's actually going to look at runtime information to determine if there's been any potential threats surfaced against that cluster. So whether that's raw security events at the IaaS layer, or perhaps more interestingly, the Kubernetes audit logs is where it can dig into the specific activity that's happening in the cluster at a Kubernetes native level and look for things that might be suspicious. And this is where it can really provide value in the sense that if you're not aware of the type of activity within a Kubernetes cluster that may be deemed suspicious, it can actually surface things that you should go and take a look at. So specifically, the recommendations that it's providing today, again, initially around cluster hygiene, so setting authorized IP ranges, which we'll talk about in a second, enabling Kubernetes RBAC, and ensuring that you're upgrading to non-vulnerable Kubernetes versions. So this is actually a related recommendation to the one that we talked about in the advisor context, where if we know that there is a security vulnerability in a previous version of Kubernetes, we will actually surface that to you specifically within Security Center, so that you'll know that not only are you running an unsupported version, but you're running an unsupported version that has a vulnerability. So making sure that that is very clearly flagged. And then on the runtime side, there's a series of potential threats that Security Center is going to monitor for, again, using those different logging sources that I mentioned in the previous slide, and use that to surface as things that you may want to go investigate. Now, there are valid use cases for some of these things. There are valid use cases for things like privileged containers, but there's also many cases where that can be indicative of a threat. And so Security Center is trying to flag those for you so you can go take a look at them, validate that indeed those were valid requests, and if not, do something to shut it down. So really surfacing our knowledge of what is potentially suspicious within a Kubernetes cluster, so you have a sense of what to go investigate across all of the different data streams that are coming in. So let's talk about one of the specific recommendations that you may see within Security Center for hardening of your cluster, and that is to set up authorized IP ranges. So this is really under the general idea of limiting access to the Kubernetes API server. So as background, any AKS cluster that you create by default will have a public IP associated with its control plane. And so when you're using kubectl to talk to your cluster endpoint, that's hitting a public IP that we have created for you within Azure. Now, obviously, you need to authenticate to that cluster based on the credentials that you acquire from the service, but it is still from a networking perspective, it is exposed as a public endpoint. And so typically you'll want to lock down access, network access to that endpoint. And you can do that in one of two ways within AKS. The first, and the one that you'll see recommended as a default option in Security Center, is using authorized IP ranges. So this is effectively a firewall where you can provide us with a set of trusted IP ranges that you want to allow access to that API server, and we will apply those firewall rules within the managed infrastructure. The second option, and one that went GA relatively recently, is to use private clusters. So this is based on Azure Private Link, and this will fully limit access to that API server to only callers that are within the virtual network. So the agent nodes and other resources that you might have within directly within the virtual network, or peered VNets, potentially on-prem via express route. So that's an even more lockdown capability, but another way to limit access to that API server endpoint. Now, as I alluded to, those methods are strictly for controlling network access. They don't have anything to do with authentication or authorization. That's where you'll want to introduce Kubernetes RBAC, which is turned on by default for all AKS clusters, but then also associated with Azure AD as a authentication mechanism, and set up the appropriate RBAC roles and role bindings within the cluster to ensure that only the right set of users are doing the operations that you want to allow. Okay, so let's take a look at how those Security Center recommendations get surfaced here. So we're back here in the portal, again, inside the AKS blade, and as we saw before, we've actually consolidated the Security Center recommendations with the Azure Advisor recommendations so that you can see them all here in one place for this specific resource. So you can see the authorized IP range recommendation here, and the impact is listed as high, so probably something that I want to take pretty immediate action on. And if I drill in on that, I get a security lens on that recommendation. So it's going to list out some of the potential threats that I need to be worried about. It's actually going to highlight not only the impact but also the expected effort, and we'll see actually how easy it is to do here just in a second. And then it's going to suggest a set of remediation steps. And again, similar to the pod disruption budget example that we saw before, that's going to link me out into a detailed doc that's going to describe how this feature works and how I can go ahead and apply it within my environment. So let's take a look at how we'd actually go do that. So what I'm going to do is look at this cluster that I've got running here, and I can just do a simple kubectl command just to show that I can access the API server and pull nodes. And we'll just take a look at my current IP address here on my laptop. This is the public IP address that I'm showing up as when I'm contacting that AKS API server endpoint. And just to show how we can lock this down, we'll take a look at another location that I might access it from, which is the Azure Cloud Shell, which is obviously running inside of the Azure environment. So here I'm going to have a different IP. And so what I'm going to do is actually lock down access such that I can only reach the cluster locally from my laptop, but not from the Cloud Shell. So now I'm going to update the API server's authorized IP ranges to limit access to only my laptop's IP address here. So this will block access from the Azure Cloud Shell and anywhere else that I might want to try to hit that API server from. So I'm going to do AZ AKS update. I'm going to give it the name of the cluster, the resource group that cluster is running in, and then I'm going to set this API server authorized IP ranges value. And this actually accepts a list of CIDR ranges. So if I have one or more IP ranges that I want to give access to, I can do that. In this case, I literally just want to set access for my laptop, so I'm going to give it a /32, which is just for that IP address. And that's going to go ahead and run for a few minutes to update the firewall rules, and then we'll be able to see that I can still access it from here on my laptop, but not from within the Cloud Shell. Okay, so that's now completed, and so if I rerun get nodes here, you can see that I can still hit the API server from my laptop. But if I jump over to the Azure Cloud Shell now and try to get nodes, it will sit here forever because it is blocking my access. So eventually the kubectl command will time out, and this is because the access from all other IP addresses outside of the one that I added to the firewall rules is now blocked. So I've really constrained network access to this cluster, and by virtue of doing that, improved its security. Okay, so far we've talked about the ways in which we are surfacing Kubernetes best practices through things like Azure Advisor and Azure Security Center, such that you can consume those recommendations in advance and make sure that your cluster and your applications are in the best possible state for high availability and reliability. There's always going to be cases where a recommendation is missed or something goes wrong, and now you're in a state where there's a problem with your cluster, there's a problem with the applications that are running inside of it. And so we're trying to take a lot of those recommendations and best practices and apply them to doing diagnosis on your cluster as well through an experience that we call AKS Diagnostics. And so the idea here is to provide a set of self-serve troubleshooting tools built into the Azure portal, again, much like Advisor, built on top of telemetry that we have about your cluster, combined with the experience that we have from working with literally thousands and thousands of customers and the associated support cases that many of those customers have created. So what we've found is many of the support cases that customers create are ultimately root cause to something where they didn't configure their cluster correctly, or they didn't configure their applications correctly. And so we can actually identify those issues in advance and allow you to take the appropriate action to avoid having to create a support case in the first place and to get your cluster back into a good working state. So a few of the examples that you'll see in that diagnostics experience today are around pod evictions, very restrictive firewall rules, which is a common source of issues in terms of how the cluster operates, issues with DNS resolution, subnet IP exhaustion. There's a whole series of additional checks that we perform against the cluster. But I want to dig into one specifically because this has been a very common source of issues for customers and something that, again, much like pod disruption budgets, is not something that is obvious as you are learning Kubernetes for the first time, but it's something that's really critical to understand in order to ensure that your cluster operates correctly and that your applications stay available. And that is the pod evictions or kill recommendation or troubleshooting step. Now, the critical background here is to understand how the Kubernetes scheduler works. So when you provide a deployment and the associated pod specs, the scheduler is going to try to find a place to run those pods within the cluster, but it's going to do that based not on the unused capacity at the time that you're making that deployment request, so not in terms of what's actually being consumed, as you might view within a monitoring tool, for example, but based on what is unallocated within the cluster from the scheduler's perspective, so what is unreserved in terms of capacity. So when you deploy a pod and its associated containers into Kubernetes, you have the opportunity to set what's called a resource request. And that allows you to reserve a set of capacity in terms of memory and CPU and potentially other resources for that application to be able to run correctly. But that's an optional field. And so if you don't set it, then the scheduler is going to attempt to schedule more and more pods onto a given node because it doesn't actually know whether that pod requires 100 megabytes of RAM or 500 megabytes or a gigabyte. And so it's just going to continue to schedule things there. And then ultimately, as those applications attempt to run and consume more memory, they will hit the edges of what that node can actually manage to run. And so the system will then attempt to start shutting down pods to reclaim resources and ensure that the node can stay healthy. Now, there are very good use cases for that. You may want to be running some low priority pods where if there is capacity available, that they should be able to consume it. But in a lot of cases, you actually want those pods to be running continually. You want them to be remaining available. And so when they're getting killed for lack of resources, that is impacting the availability of your overall application. And so if we detect that we are seeing significant number of kill operations and evictions of pods within the cluster, that is something that we're going to surface through the troubleshooting and diagnostics tool. So just to show how some of those diagnostic recommendations are getting surfaced, let's take a look again here in the portal, and specifically this time we're going to drill in on the diagnose and solve problems menu item. And this is going to surface a couple of different buckets of potential issues, and you can see some descriptions here of the types of issues that I might be able to diagnose based on these two different buckets. So in this case, I'm going to drill in on cluster insights. And you're going to see that it runs a series of checks against my cluster. And again, this is based on the telemetry that we have about the operations of your cluster. And so you can see a bunch of the things that have passed here, as well as in a moment we'll see some of the failures and warnings that I need to be concerned about. And so you can see that killed pods that we were just discussing, and I can drill in here on more info and get a whole bunch of detail about when this happened, the image that was running, the specific pod, the namespace that it might have been running in, number of restarts, and so on. And so that gives me a bunch of diagnostic information that I can then go and connect to my logs and troubleshoot directly against the cluster. I'm also getting a set of pointers here out to documentation, much as we saw with the advisor and the security center recommendations. And interestingly, in this case, we're actually surfacing this particular diagnostic in two different locations. So the set of pods being killed, so obviously from a sort of a pod lens, but then also in terms of the node resources. So in this case, there's this one particular node that is seeing significant memory pressure, again, as a result of that same deployment that was not setting a resource request. And so that gives me another lens into the problem and how I may go about solving it. In fact, there's a couple of different recommendations here for what I can do next as potential action. So again, a great way for best practices to get surfaced in the context of a problem that you might be seeing in the cluster, and a way for you to learn how you can apply some of those recommendations to both get out of the current situation as well as ensure that you don't get into it again. So wrapping up, it's clear that Kubernetes is complex and that there is a ton to learn, not only in the concepts and capabilities of the platform, but how best to leverage them to deliver highly available, reliable, and scalable applications. So what we're looking to do in Azure and AKS is to give you hints and guidance along the way so that you can discover those capabilities and concepts that you may not have been aware of, and as particularly ones that are most applicable to your environment based on the telemetry that we have and the experience that we have working with thousands of customers running Kubernetes on Azure. And so today we've looked at a few different ways that you can consume those best practices across Azure Advisor, Security Center, and AKS Diagnostics. And there's going to be a lot more investment coming here in the coming months. So I would encourage you to follow along as we improve the service and provide more guidance on Kubernetes best practices. You can follow along at the release notes that we push out every week, as well as the roadmap that we maintain on GitHub, which shows all of the investments that we have coming over the next few months. So with that, I will say thank you for attending this virtual session and hope that you enjoy all the other sessions at Build 2020.